Hi, I am Oğuzhan. This is an overview of our paper titled BRAVE, Broadening the Visual Encoding of Vision Language Models. One common theme in current vision language models, or VLMs, is to combine a vision encoder and a language model linked by a bridge network. From a given image, the VLM extracts features using the vision encoder. The features are processed by the bridge network and then given to the language model to output predictions for different tasks, such as captioning or visual question answering. Despite recent advances, VLMs still have important shortcomings. On the language side, the models are susceptible to hallucinations and logical errors, and on the vision side, VLMs are limited by the encoders, causing feature blindness and visual hallucinations. Our focus in this work is on the visual understanding issues of VLMs. As motivation, let's examine a recent challenging benchmark, MMVP by Tong et al. It uses image pairs with small visual differences. This exposes the struggles of recent VLMs to detect these changes, hence their visual blindness. We start evaluating instruct and lava by asking if a hand is using the mouse in this image. The answer is yes for the first image and no for the second. While instruct correctly answers both cases, lava incorrectly responds no to both images. In another example, asking if the butterfly's feet are visible, this time instruct fails while lava succeeds. And when asking if the truck door is open, both methods fail. These models use different vision encoders, namely EVA and CLIP, which extract different representations from images. However, neither consistently provides correct answers. Overall, the pairwise accuracies are below the random guess level of 25%. We introduced a new method called BRAVE, which consistently outperforms recent approaches by improving visual representations. To enhance the visual capabilities of VLMs, we leverage different representations. And as a well-known idea from machine learning, each representation can yield different generalization properties. Then we ensemble them for a more complete representation. Our first step towards an effective ensembling is to benchmark several vision encoders to identify their strengths and weaknesses. For this, we evaluated 8 vision encoders with different inductive biases due to differences in training objectives, datasets, and model sizes. This includes CLIP, DynoV2, VITE, and more evaluated on several captioning and VQA tasks. We find that no vision encoder excels consistently across tasks. This suggests that relying on a single encoder in a VLM is inherently limited. Additionally, encoders with different biases can perform similarly, hence various cues can be used to tackle the tasks. This leads us to ask, can we broaden the visual capabilities of VLMs through combining vision encoders with different biases? And we developed a BRAVE framework to do this efficiently. Here is how it works. First, we extract visual features from multiple frozen vision encoders. Then these are linearly projected and concatenated. We then combine the features using a multi-encoder querying transformer or MEQ-former, an extension of Q-former. It's a transformer module that interacts with the visual features through cross-attention layers, hence resampling them. It uses learnable queries and a text prompt to extract task-aligned visual features. And this is a closer look at its architecture, which consists of a set of self-attention, cross-attention, and feed-forward layers. Finally, the features resampled by MEQ-former are fed as input to a frozen language model. To train the model, we follow the standard practice of first pre-training on large mixed-text data and then fine-tuning on downstream tasks. During pre-training, we keep all the vision encoders and the language model frozen, resulting in training 1% of all parameters. Furthermore, the MEQ-former output has fixed size, enabling scalability to several encoders. We show that BRAVE achieves state-of-the-art performance for several tasks. This includes COCO captioning, no caps null object captioning, VQA V2 for general VQA, OK VQA which requires external word knowledge to answer the questions, GQA that measures spatial reasoning capabilities, and VizQA that has questions from people who are blind. These benchmarks cover different aspects of VLMs, helping to reveal their strengths and weaknesses. Furthermore, we improve robustness against visual hallucinations and blindness issues as measured by the POP and MMVP benchmarks. POP on the left tests for hallucinations by querying non-existent objects. MMVP shown on the right uses image pairs with small visual differences confusing the VLMs, as mentioned before. This spider chart illustrates BRAVE's improvements on all tasks shown in blue compared to recent baselines BLIP2, instruct, and lava. Quantitatively, BRAVE shows significant improvements on captioning benchmarks, achieving top results on no-caps evaluation sets for both out-of-domain and overall benchmarks. For COCO captioning, BRAVE ranks second after PALI while using fewer trainable parameters, less pre-training data, and lower image resolution. For visual question answering, BRAVE shows strong performance overall, ranking first in 6 out of 7 evaluations and second for VQA V2. Additionally, BRAVE improves robustness as measured by the MMVP and POP benchmarks. For more results, including qualitative analysis, ablations, and insights on vision encoders, please refer to the paper. Thank you for your attention.